Imagine a country where millions of people live below the surface of the sea. Not underground, not in submarines, but in ordinary cities with schools, highways, airports, and train stations. All these cities sit on land that the ocean wants to reclaim every single day. That country is the Netherlands. And if you have never really thought about what that means, consider this. Take the entire state of Florida, push it 3 feet below sea level, and then tell 40 million people to keep living there while the Atlantic Ocean presses against every coastline, every river mouth, and every canal. That is the Netherlands, a nation that exists not because geography allowed it, but because engineers, builders, and an entire society decided it would. For centuries, the Dutch have been fighting water. They built dikes and pumped out lakes. They drained marshes and turned soggy floodplains into farmland. Windmills were not decorations. They were survival machines, spinning day and night to push water out of land that would flood the moment anyone stopped paying attention. But despite all that effort, the sea kept reminding them who was really in charge. On the night of January 31st, 1953, a massive North Sea storm combined with a high spring tide and pushed a devastating surge into the southwestern coast of the Netherlands. Dikes failed, seawalls crumbled, water poured into towns, farms, and villages while people slept. By the time it was over, more than 1,800 people were dead. Entire communities had been erased. Roads, railways, bridges, power systems, and livestock were gone. The flooding reached areas that had not seen seawater in living memory. It was the worst natural disaster the Netherlands had experienced in modern history, and it exposed a terrifying truth. The country's patchwork system of old dikes and local barriers was not strong enough to protect a modern nation from the full power of the North Sea. The response was not grief alone, it was engineering fury. Within weeks, the Dutch government launched an investigation. Within months, a national commission delivered its answer, a plan so ambitious that it would take decades to complete. The idea was not to patch the old walls. The idea was to fundamentally redesign the entire southwestern coastline, close the estuaries, seal the river mouths, build a connected chain of dams, barriers, sluices, and storm surge gates powerful enough to hold back the ocean for generations. They called it the Delta Plan, and what followed became one of the most extraordinary construction campaigns in human history. The problem facing Dutch engineers after the 1953 flood was not a single broken wall. It was an entire coastline full of openings. The southwestern Netherlands is not a straight shore. It is a maze of river mouths, tidal estuaries, islands and channels where the Rhine, the Meuse, and the Scheldt rivers meet the North Sea. Every one of those openings was a door the ocean could push through. And in 1953, it pushed through almost all of them at once. The Delta Commission studied the geography and identified the weak points. There were too many estuaries exposed to storm surges. Too many old dikes built to different standards by different local authorities over different centuries. Some were medieval, some were maintained, some were neglected. The system had no unity, no coordination, and no ability to resist a once-in-a-century storm. The Commission's conclusion was radical. Do not repair the old defenses one by one. Instead, shorten the entire coastline by closing off the most dangerous sea inlets with massive new dams and barriers. Fewer openings meant fewer places the ocean could attack, and every closed estuary would protect hundreds of kilometers of older dikes behind it, reducing risk across the entire region without having to rebuild every local wall. But before any dam could be designed, engineers needed to understand what lay beneath the water. Survey vessels moved into the estuaries and channels, measuring depth, current speed, tidal range, and sediment behavior. Geotechnical teams drilled into the seabed to study what the foundations would rest on. Sand, clay, peat, and rock layers were mapped and tested. Oceanographers recorded wave heights, storm patterns, and seasonal changes. Hydrologists calculated how much river water still needed to flow out to sea, so the land behind the dams would not flood from the inside. This was the invisible stage of the project. No concrete was poured, No steel was lifted. But without this phase, every structure built afterward would have been a guess. The engineers were learning the personality of every waterway, every current, every tide, and every layer of ground beneath it. They were figuring out where the seabed was strong enough to anchor a dam, where currents would fight hardest against closure, and where environmental systems depended on the natural flow of salt water. The Delta Plan was approved by Parliament in 1958. It authorized the construction of 13 major structures across the southwestern delta. The largest public works campaign the Netherlands had ever attempted was about to begin. The first structures in the Delta Works were not the most famous, but they were the most urgent. Engineers started with the smaller, more manageable closures to protect the most vulnerable areas quickly and to test construction methods that had never been attempted at this scale. Every dam built in those early years became a lesson for the next one. The Zand Creek Dam came first, completed in 1960, closing a narrow tidal channel between two islands. It was short compared to what would follow, but it proved that a full tidal inlet could be sealed using a combination of concrete caissons, sand fill, and rock protection. Workers and engineers watched the water fight back as the gap narrowed, the current accelerating through the shrinking opening with increasing force. That behavior would define every closure in the Delta Works. The ocean does not give up its channels quietly. As the gap gets smaller, the water moves faster, harder, and more violently until the final section is sealed. Next came the Veersegat Dam in 1961, blocking a wider inlet and creating a new freshwater lake behind it. Then the Grevelingen Dam in 1965, separating two major water basins. Each project required its own approach because no two estuaries had the same depth, the same current, or the same seabed composition. Some foundations sat on dense sand. Others rested on soft clay that had to be stabilized before any weight could be placed on it. Engineers developed a method of sinking massive prefabricated concrete caissons into position. These hollow box structures were built in dry docks, floated to the construction site, positioned precisely using tugboats and anchoring systems, and then sunk onto prepared foundations by flooding their internal chambers. Once in place, they were filled with sand and sealed together to form a continuous wall across the waterway. Around each caisson, crews dumped enormous volumes of rock, gravel, and specially shaped concrete armor blocks to protect the base from erosion. Cranes worked from barges. Divers inspected underwater joints. Survey teams checked alignment constantly because a single caisson placed even slightly off position could compromise the entire structure. The work was brutal, weather-dependent, and dangerous. Construction seasons were short. North Sea storms could shut down operations for days. Equipment failed in saltwater. Currents shifted unpredictably. But dam by dam, inlet by inlet, the southwestern coastline was being redrawn. Openings that had carried deadly storm surges in 1953 were becoming solid barriers of concrete, steel, and stone. The sea was losing its doors. By the early 1970s, the Delta Works had closed several inlets, and the engineers were preparing for the biggest closure of all, the Oosterschelde, the largest estuary in the southwestern delta. The original plan was simple. Seal it completely, just like the others. Build a solid dam across the mouth, block the tide, and create another freshwater lake behind it. But something unexpected happened. The people said no. Fishermen whose families had worked the Oosterschelde for generations warned that closing the estuary would destroy one of the richest shellfish grounds in Europe. Oyster beds, mussel farms, and marine ecosystems that depended on the daily rhythm of saltwater tides would die behind a solid wall. Environmentalists joined the fight. Scientists confirmed that the tidal ecosystem inside the Oosterschelde was unique and irreplaceable. The political battle was intense. On one side stood the engineers with a proven method and a deadline. On the other stood an entire regional economy and an ecological argument that could not be ignored. The compromise that emerged changed the entire project. Instead of a solid dam, the government authorized the construction of a storm surge barrier, a structure that would stay open under normal conditions. This allowed tides, saltwater, fish, and currents to pass through freely, but could close completely when a dangerous storm approached. Nothing like it had ever been built before. The Oosterscheldekering became the centerpiece of the Delta Works and one of the most complex engineering structures on Earth. Engineers designed 65 massive concrete pillars, each standing up to 40 meters tall and weighing 18,000 tons. These pillars were cast in a specially constructed dry dock, a temporary basin large enough to build the pillars in rows before flooding it and floating them out to sea one by one. Each pillar was towed to its precise position in the estuary, lowered onto a prepared foundation of compacted sand and stone mattresses, and set into place with centimeter accuracy. Between the pillars, enormous steel gates were installed, 62 in total, each capable of being raised to allow water through or dropped to seal the barrier shut. Hydraulic systems powered the gates. Sensors monitored water levels. A central control system connected every gate to weather and tide data so the barrier could respond to a storm within hours. The construction took nearly 10 years. Thousands of workers, hundreds of vessels and engineering methods invented specifically for this project. When it was finished in 1986, the Oosterscheldekering was not just a dam. It was a machine, a programmable wall that could decide when to hold back the sea and when to let it breathe. The Oosterschelde solved the problem of protecting a tidal ecosystem, but the Delta Works still had one enormous gap left open. The Nieuwe Waterweg, the main shipping channel leading directly into the port of Rotterdam. And Rotterdam was not a detail that could be worked around. It was the largest port in Europe, a gateway for oil tankers, container ships, and cargo vessels feeding supply chains across the entire continent. You cannot build a solid dam across a channel that handles tens of thousands of ship movements every year. You cannot even build a permanent barrier with gates like the Oosterschelde, because the shipping lane had to remain completely wide open under normal conditions. No pillars, no obstacles, and no restrictions to navigation. Engineers needed something entirely different, a barrier that did not exist until the moment it was needed. The answer was the Maeslantkering, and when you see it for the first time, it is difficult to believe it is real. Two gigantic steel arms, each longer than the Eiffel Tower laid on its side, rest in dry docks on opposite banks of the waterway. Each arm is connected to a curved steel gate the size of a city block. Under normal conditions, the arms sit parked in their docks, completely out of the way. Ships pass through the open channel without even noticing the barrier is there. But when sensors detect a storm surge that will push water levels more than 3 meters above normal, the system activates automatically. The dry docks flood. The hollow steel gates begin to float. The massive arms swing outward on their hinges, rotating across the water like two slow cathedral doors closing from opposite sides. When they meet in the middle, the gates are flooded further until they sink to the riverbed and form a solid steel wall across the entire channel. The disconnection from human hands was deliberate. The Maeslantkering is operated by a computer system that monitors weather data, tide levels, and storm models continuously. When conditions cross the threshold, the system triggers the closure sequence without waiting for a phone call or a committee decision. Engineers understood that during a real emergency, speed and certainty matter more than human judgment. The system was completed in 1997 and has been tested regularly ever since. Every year, the arms swing shut in a controlled exercise to verify that hydraulics, sensors, buoyancy systems, and control software still function exactly as designed. Because in a country where the sea is always waiting, a barrier that fails to close is worse than no barrier at all. Today, the Delta Works stands as a connected system of 13 major structures stretching across the southwestern coast of the Netherlands. Dams, sluices, locks, storm surge barriers, dikes, and levees working together as a single defense network. Some are solid walls that permanently closed tidal inlets. Others are movable gates that open and shut depending on conditions. Some manage river flow. Others block ocean surges. But none of them operates alone. The system works because every piece was designed to support the others. Close one estuary, and the pressure shifts to the next. Strengthen one barrier, and the dikes behind it can hold longer. The American Society of Civil Engineers recognized the Delta Works as one of the 7 modern wonders of the world, alongside projects like the Panama Canal and the Channel Tunnel. And unlike most engineering landmarks, the Delta Works is not a monument to a single achievement. It is a monument to a decision that an entire nation made together and then spent 50 years building. But the story does not end with the last dam. The Dutch know better than anyone that water does not stop planning its next move. Sea levels are rising. Climate models project stronger storms, higher surges, and heavier rainfall in the decades ahead. The engineering that saved the Netherlands in the 20th century may not be enough for the 21st, so the country launched a new program called Room for the River. Instead of only building higher walls, engineers are now giving water more space to spread safely during floods. Floodplains are being widened. Dikes are being moved back. Some low-value farmland is being deliberately designated as overflow zones. The philosophy has shifted from pure resistance to managed adaptation, not abandoning the fight against water, but changing the terms of the battle. For Americans watching coastlines erode in Louisiana, floods worsen in Houston, and hurricanes push deeper into communities from Florida to the Carolinas, the Dutch example is not a foreign curiosity. It is a blueprint that asks an uncomfortable question. What happens when you stop treating every flood as a surprise and start treating water as a permanent adversary that demands a permanent strategy? The Netherlands did not build the Delta Works because the engineering was easy or the money was available. They built it because a single night in 1953 proved what happens when a nation ignores the ocean. Every dam, every barrier, every gate in the system carries the same message. The sea never stops, and neither can the people who choose to live beside it.